Good morning, students. Today we talk about atomic structure part third. This is your part third. Electromagnetic waves. Basically, the term electromagnetic is made up of two words, electron magnetic. So, how we define these waves? Those waves which are made up of electric as well as magnetic fields. Electric field is generated with the help of charge, while magnetic field is generated by charge when in motion. When our charge is in acceleration, then magnetic field will generate. So basically, how we define these electromagnetic waves? The wave which is made up of electric and magnetic field called electromagnetic waves. What are the example of EM waves? Basically, sunlight is the example of electromagnetic wave. Okay. Next, you can see here the pictorial show the EM wave. The theory of electromagnetic wave was given by Maxwell. So what are the properties of electromagnetic waves or radiations? They are having electric and magnetic field which is produced by oscillating charged particles. Oscillating means to and fro motions of charged particles. These fields are perpendicular to each other. So basically there are three candidates. One is electric field, magnetic field and direction of propagation. All three are mutually perpendicular to the each other. That made electromagnetic radiation. Second important point to note is that they do not need any media to travel, like sound waves. If you see, the sound waves are not considered as electromagnetic radiation because it is an example of mechanical waves and it requires media for traveling. In space, we can't talk with each other. Why? Because sound waves is a mechanical waves, but but sunlight can travel in vacuum also. The very good example is sunlight, which travel from the sun and reaches to earth and cover a several meter distance. Some of the places it never have any kind of media, even it reaches to the earth. That is the electromagnetic radiation. Sunlight is the example of electromagnetic radiation, while sound waves are the example of mechanical waves. So what we conclude that electromagnetic wave is made up of two fields, electric and magnetic field. Both are mutually perpendicular to the direction of propagation. And second important point, electromagnetic radiation never required any media to travel. Come to the next. What are the characteristics for electromagnetic radiations? So there are four characteristics which I explained: wavelength, frequency, velocity, wave numbers. Wavelength is represented by lambda, the inverted Y-like symbol. Frequency is represented by curly V, small v. Velocity is represented by capital V. Wave number is represented by nu bar. This is nu. And if we put a bar here, then it becomes wave number. Okay. So first, before going on these characteristics, first see the structure of wave, you can see here, this is a characteristic. These are the characteristics which are shown by this wave. You can see here, this is 0, that is your base. If you see this part, the part above the 0 is called crest, and trough, this is the depth part of the from the 0. So how we define this lambda wavelength? The minimum distance between two nearest trough or crest. The minimum distance between two nearest means neighboring. The distance between two nearest trough is called lambda, while this complete cycle is called single wave. From that to that, or we can also write this lambda is a wavelength. Length is the word here. That means lambda measured in meter, centimeter, angstrom, picometer. These may be the units of this wavelength. Okay, so it is more clear from this pictorial. Wavelength is defined as the distance between two neighboring crest or trough of a wave, and it is denoted by lambda, and unit may be meter, nanometer, angstrom, but the common unit which we use in this chapter is nanometer. That means 10 raised to power minus 9 meter. What about the next characteristic, that is frequency? It is defined as the number of waves which pass through a particular point within a 1 second. So within a 1 second, one wave, if we take an example of two different waves, in 1 second, wave A pass about 100 waves are passed through a single point, and within 1 second, if 200 waves are passed within a 1 second, then the waves which pass 200 within a 1 second must have greater frequency. Okay, now unit of frequency. Basically, frequency is measured in second inverse. That means time inverse, or mainly represented by hertz. That is represented by capital H and small z, Hz. Hertz. Next one is velocity. As you know from the classical formula of velocity, velocity is equal to distance upon time, and here in case of wave, the total distance is considered to be the lambda. Okay. Lambda by t will give us velocity. But on the other hand, we have calculated amount of the velocity of light, we can say speed of light in vacuum, that already calculated, and you must learn this data, 3 into 10 raised to power 8 meter second inverse, and that is denoted by V. Okay, next is suppose what is the unit of this velocity? Meter per second. As we know, same unit that belongs to classical velocity. Come to the next, wave number. Basically the total number of wave number, basically the reciprocal of wavelength is called wave number. The reciprocal of wavelength is called wave number. Okay, wave number is defined as the number of wavelength per unit length You can also write this definition as the reciprocal of wavelength is called wave number. So the formula become nu bar is equal to 1 upon lambda. That is the basic formula of wave number. Okay. So what are the relations? Sometimes examiner will ask that what is the relation between velocity and frequency, and you have to write c is equal to c is basically that amount 3 into 10 is to power 8 meter second is the c. Sometimes may written as a c if it is a speed of light, then it denoted by small c. If it is normal velocity, then it denoted by v. So c is equal to nu lambda, that means frequency, and that is your wavelength. That is the relation between c and lambda, or we can say the relation between frequency and wavelength. Next theory, which is put forward by Planck's, that is Planck's quantum theory. So basically, we talk two theories which later explain the dual behavior of matter. Okay, we already talked about the electromagnetic wave theory that was put forward by Maxwell. Now we talk about Planck's quantum theory. So what Planck say that radiation energy is emitted or absorbed not continuously but in a discrete, that means discontinuous manner. Okay, and in form of packets of energy called quantum. In case of light, they are called photon, but in other cases, these packets are called quantum. If they are large in number, then they are called quanta. That's why this theory named as Planck's quantum theory. The word quantum means packets of energy. In simple way, if we elaborate this theory, then what we say that whenever radiation is emitted or absorbed, always in discontinuous manner in a form of small packets of energy called quantum. That is the basic theme of this theory. So quantum theory, that is Planck's quantum theory, also provide the data about the energy of each packet. So according to Planck's energy of a quantum is equal to h nu. H is Planck's constant here, whose value equal to 6.626 into 10 to power minus 27 joule seconds. The energy of each quantum is directly proportional to the frequency of radiation. That means E is directly proportional to nu. And if we eliminate this proportionality sign, then we have to put a constant here, that is H. And having this data, so you have to memorize this value of H because it is having great importance to solve the numericals. Next, energy is always emitted or absorbed as a integral multiple of quanta. That means half 3 by 4 1 by 4 quanta is not absorbed by body. It must be in a whole unit. That means 1 2 3 and 4. Is not possible that half of the quanta is absorbed by any substance or uh, released by any body. Is not possible. So it is a whole unit. Next one is Photoelectric effect. Phenomena explained by the photoelectric effect. So basically, what is photoelectric effect? Yes, we need some correction here. We have to change the order here. Dual behavior, photoelectric effect. Yes, you can see here the term photoelectric effect, the phenomena of ejection of electron from the surface of metal when light of suitable frequency strike. It is called photoelectric effect. We can define it in our term as the phenomena of ejection of electron from metallic surface whenever sunlight is struck to it. Photo means light. Basically, photo term is used for sunlight and electric is used for the electrons. So ejection of electron if take place when a sunlight is struck to the metallic surface. That phenomena is called photoelectric effect. Okay, and the electron which is ejected during photoelectric effect called photoelectrons. Next, so basically photoelectric effect is explain the Planck's quantum theory. Basically, it explain the support the Planck's quantum theory. So there are two views of the scientist at that time, that the matter has wave nature as well as particle nature. Electromagnetic radiation is fall into category of wave nature. Electromagnetic radiation theory, EM wave theory. There are two theories. One is EM theory, another is for Planck's quantum theory. EM wave theory support the wave nature, while Planck's quantum theory support the particle nature. EM wave theory was supported by diffraction, okay, refraction, etc. While photoelectric effect supports the Planck's quantum theory. So basically, there are two views towards the nature of matter. These are particle and wave natures. Okay, come to the next. Planck's quantum theory explanation according to photoelectric effect. So what are the observations which are made by photoelectric effect? When a beam of light falls on a metal surface, electrons are ejected immediately. Which electron? Those electrons which are present in outermost shell. Outermost shell means valence shell. Those electrons which are present in outermost shell or valence shell, they are loosely bound with the nucleus and they are easily removed with the help of particular energy radiation. Next, the number of electrons ejected is proportional to intensity of brightness of the light. Okay, you can you can understand this as you can understand is that you can see here the important conclusion which are made through this photoelectric effect. Threshold frequency is a very important definition. The minimum frequency which is required to eject an electron is called threshold frequency. Okay. Next, there is a wave function that is represented by WO, W naught, the minimum energy which is required. The difference in between threshold frequency and work function is there is a minimum frequency and there is a minimum energy required to eject an electron from metallic surface called photoelectric work function. So basically we can write W naught is equal to H nu naught. So energy of ejected electron is H nu minus nu naught is equal to half mv square. That is kinetic energy of that ejected electron. Okay, we can see it as we can see it as I explain it. You can see here total energy which comes from sun in form of sunlight is utilized to carry out two functions. One is it is utilized as a work function, that is E naught, or work function, that is W naught. Both are same thing, and remaining portion of that energy is converted into kinetic energy. So if we have to find the kinetic energy, then we have to carry this term to the opposite side. So H is a common, V minus V naught. This is the expression for the kinetic energy of ejected electron. So these are some important conclusions which are made through this photoelectric effect. Now, some of the phenomena which can be explained by this photoelectric effect, phenomena which are explained by Planck's quantum theory, which are explained by Planck's quantum theory. You can see here one is okay. You can see here. So there are two phenomena which can be explained by Planck's quantum theory. One is photoelectric effect. We already discussed it. Another is black body radiation. So black body is a imaginary or ideal body which emit and absorb the frequency of all kind of radiation. That is called black body. A hot iron rod can behave as a black body. It's not perfectly ideal, but it may behave as an ideal black body. Some of the scientists think about this black body resemble this consider black hole as a type of black body. Okay. That was further explained by Stephen Hawking and other scientists. So black body is ideal and exists in somewhere in the universe. Okay, and which emit or absorb radiations of all frequencies. That is black body actually. Next one is dual behavior of electromagnetic radiation. We already talk about the two different behavior, two different characteristics of a matter. So you can see a dual behavior of electromagnetic radiation. The light possesses both particle and wave like properties. Light has a dual behavior. Whenever radiation interacts with the matter, it displays particle like property like black body radiation, photoelectric effect. Okay. And wave like nature, it exhibit and propagate to form interference or diffraction. These two phenomena explain the wave nature. Come to the next. So mathematical explanation for this dual behavior of matter. is given by de Broglie by the equation P is equal to h upon lambda. P is your momentum, h is your Planck's constant, lambda is your wavelength. So how we obtain this final expression from Planck's quantum theory? E is equal to h nu, and from Einstein equation E is equal to mc square. If we combine both the equation first and second, we got this one. Finally, h upon lambda is equal to p. P represent the particle nature. Momentum is possessed by a particle, this so it represents the particle nature, while lambda is a characteristic of wave, so it represents the wave nature. So both are together in a single formula. That's why it represents the dual behavior. So this derivation is so important, and that equation is also important. That was given by de Broglie. Come to the next, that is a spectrum. You can see here how we define this spectrum. The series of color bands is known as spectrum. Series of color bands. Color is actually the different frequencies of the wavelengths called spectrum. Rainbow is a kind of a spectrum. You can visualize it. So spectrum is just like a rainbow. Okay. The spectrum is of two types. One is continuous and another is line spectrum. If spectrum having number of wavelengths, that means different kind of colors like blue, green, yellow, red, vibrio. You know the vibrio, rainbow colors. So it show the continuous spectrum type. While line spectra having a particular specific wavelength, that means only green, only yellow, like that. That spectra is called line spectra. So spectrum is of two type on the basis of wavelength they contain, continuous and line spectra. And another classification is there. Spectrum may classify on the basis of their source of formation, their form. So it may be emission or absorption spectrum. If a spectrum is formed by radiations emitted through a body, then they are called emission spectrum. And these radiations are absorbed before. Next one is absorption spectra. So absorption spectra is spectrum obtained when a radiation is passed through a sample material and that sample material absorbs some of the radiations. So absorption spectra is observed in form of dark and light lines. That is a characteristics of this absorption. Now the study of both kind of spectra is called spectroscopy, and spectroscopy is a branch of chemistry which deals with the study of these two types of spectra, which obtained from any atom or element. Come to the next. Our intention is only limited to hydrogen because it is related with the Bohr model. Bohr provide or study the hydrogen and hydrogen-like elements, and he also provide the line spectra of the hydrogen. You can see here each and every lines of this spectra represent a particular wavelength or frequency. You can see here the first radiation, larger will be the gap, larger will be the frequency or energy. If you see here, there are total 21 lines. If we count from 7 to first, there are total 21 lines. We also provide the formula how we calculate this. So basically in a hydrogen line spectra, there are six type of series we obtain. Lyman, Balmer, Parsons, Brackett, Pfund and Humphrey. Basically these are the six type of spectral series we obtain. Each spectral series contains several spectral lines. This is your first spectral line. This is your last spectral line. Okay. So the first spectral lines having minimum frequency, and we already know that the frequency is inversely proportional to wavelength. The minimum the frequency, higher will be the wavelength. And the last line having largest frequency and minimum wavelength. So how many you can count these lines? Each lines resemble with a particular wavelength of the frequency. Okay. We prepare a table here. So Lyman series is formed by electron during transition. If it show transition from second, third, fourth onward any cell to the first shell, that means electron may jump from any shell and reaches to first shell, and then radiations are having wavelength that fall into category of ultraviolet, and these spectral lines are called Lyman series. The conclusion is that if you find the wavelength of all these lines, then these whole wavelengths of lights are fall into which category? Ultraviolet range of the spectrum. Next, gamma series, that means rays comes from any shell third and onwards, and but reaches to only two. That means their frequency and wavelength is line visible region is similar. You can see most of the out of six, four lines are lying in an infrared region. Partition, bracket, Pfund and Ampere are lying in an infrared region. Next is on studying these spectra, hydrogen spectra, Redberg going on any conclusion and give a formula here. You can see here for the calculation of wave number, that is represented by nu bar. So the wave number is equal to R 1 by N1 square. N1 is the destination shell. N2 is the starting shell. That means electron should transition from N2 to N1. That means higher energy level to lower energy level. That means hydrogen spectra is a kind of emission spectra, not absorption. It's an emission type of spectra. Okay, and it is a type of line spectra. So if someone asks about the nature of hydrogen spectra, then you have to give answer in two lines. Hydrogen spectra is a line spectra and emission type of spectra. R having value 109,677 centimeter inverse, and you already know about the N1 and N2. N1 is the destination shell number, while N2 is the starting shell number. Come to the next. This is your worksheet. I prepared some of the well-known questions. You have to give the answer of each and every questions. I already provided the answer. You have to thoroughly read or study these questions. This is all about today lecture. We will continue our lecture on atomic structure. Tomorrow I will start the quantum model. Okay. So have a nice day and take care and stay safe at your home.